Hi, my name is Koroush Shirvan. I'm a faculty in the Department of Nuclear Science and Engineering at MIT. And today I'll talk about nuclear energy costs and innovations that matter to lower that cost. I'd like to acknowledge my research group for some of the results that we'll present in this work, as well as our entire collegial MIT community that has helped me work on nuclear power engineering topics for the past 10 years. And I'd like to acknowledge funding from various sponsors, particularly respect this work, Electric France, Excellent Generation, as well as Fortum, which are all energy utilities. So in this presentation, I will compare existing nuclear technologies to combined natural gas, argue that overregulation and perception of nuclear safety has led to uneconomical performance, challenge the philosophy that has led to unattractive cost features of near-term class of small reactor offerings, and propose innovations that matter, drawn from bottom view of nuclear costs. Today, nuclear energy makes up about 10% of world's electricity. And the majority of the world's electricity is still supplied by carbon-intensive sources. If you look at just worldwide, 30 plus countries use nuclear energy. That's roughly over 400 commercial reactors, and 95% of them are water cooled. So basically similar technology. And when you look at what's happening around the world right now, who's building the reactors, you can see China is definitely building most of them, and then India, Russia, and some other countries are building a few. With the US, of course, we're building two now after a few decades. So if you look at fundamentally what drives nuclear, which is the fission reaction, it's definitely is a step forward in humankind's search for higher energy density fuels. And it's pretty when you compare the utilization of fuel in terms of energy per mass and compare the fission to other hydrocarbons or fossil fuels. Here you can see versus natural gas, we're talking about a 70,000 times higher energy density. And this is a practical limit, not a theoretical limit. Theoretically, it would be an order of millions times better. The other thing you notice, this graph is in a log scale, not a linear scale. And you can see that if I put this in a linear scale, you can see really the difference. The other thing you notice that if you want to actually improve our energy density even further, there are technologies that we can leverage within fission that can give you even 10 times that. This is the fast reactor technologies that has been demonstrated in the US, France, Japan, China, and a lot of countries. And that energy density translates to favorable profiles. So here's a picture of 3 solar thermal plants in the US, totaling net 400 megawatt electric at 25% capacity factor versus a couple of nuclear power plants in California, providing over 2 gigawatts electric at 90% capacity factor. So you can just see the massive difference in land use, as well as the dispatchability of nuclear. Unfortunately, these 2 nuclear power plants are set to shut down short their lifetime due to just ideological differences in state of California. So the physics clearly implies that fission should dominate, and we should really, particularly with our goal of decarbonization around the world, we should be building more plants, and we should take up more than 10% of world's electricity. If I show you these 2 pictures, and if I don't tell you which one is a nuclear power plant, which one is not, it's going to be kind of hard to say, right? Even though the fission had 70,000 times the power density, they look kind of on similar scale. And unfortunately, for nuclear energy, the one on the left is the combined natural gas plant. And in fact, these 2 exact reactor types, AP1000s, were supposed to be built here on this site, but because of the cost of utility to go with the combined natural comes in at far less cost and much quicker. And so you may wonder, well, what happened to my energy density gains, and why is these structures so big and so costly? This experience of these two reactors that has gone over twice over budget and over schedule has basically destroyed any appetite that utilities have in the U.S. for large reactors like these. And so the really the hope right now in the U.S. the future of the industry really lies on balance on small modular reactors, which are smaller plants. So the utility has lower overall lower investment that they have to risk when they decide to deploy nuclear energy. So now let's look at a little deeply of why the footprints are on the same scale and why the cost is so high for nuclear. If you look at the nuclear fuel, it's form of these little pellets of 1 centimeter in height, and each of these pellets can replace 200 gallons of oil or 20,000 cubic feet of natural gas. So there's there's our great power. Then what we do here, we take these fuels and stack them in the cylindrical rods, encapsulated by zircaloy, which is a material. And then we put these in an assembly, about 300 of them. And then we take these assemblies and we have 200 of them that make up this core here in this reactor pressure vessel that's about 13 meters high and 4 meters in diameter. So you can see that the fuel itself, by volume, almost takes half this space of the reactor pressure vessel. So we still, more or less conserve that high power density. But when you look at where this pressure vessel is actually situated within the entire plant, you see that while this is actually the largest single equipment overall, it's actually a very small part of the nuclear power plant. You can see things like emergency systems here, like in the auxiliary building. You can see a containment building, and then you can see the turbo machinery side. And there's a lot of other systems this cartoon is not showing. So right off the back, when you combine an existing plant with combined natural gas, we lose factor of 2 in energy density because we're factor of 2 less efficient in terms of transferring heat to electricity. And that has to do with the fuel technology we have. It can't really operate with supercritical water or high temperature water because of material concern. So we are right off the back, limited to around 300 degrees C. So we end up with very low efficiencies compared to fossil fuels. The other thing that makes nuclear more costly than the actual capital cost is it's an extremely regulated industry. And there are some good reasons for it, because nuclear hazard does not exist in a natural gas plant. And nuclear hazard is what's unique about it is that when the fission reaction happens, the fission remain radioactive and actually they remain generating heat. So if you shut down the fission reaction, you're continuously generating power. And that's why you have these emergency cooling and auxiliary cooling system, because you have to constantly remove heat from the reactor core. And typically you have 4 or 5 of these and diverse systems as well, which ends up in ballooning the cost. The other reason those plants I showed you in the US were so overcost and overrun, simply because in the US we just haven't built anything, and whether it's solar project, wind project, natural gas project, if it's first of a kind, you're always going to have a lot of first of a kind issues. So that was the story about the capital costs comparing with natural gas. Let's look at how do we operate these reactors compared to natural gas. Look at a combined natural gas plant, you roughly have 40 people on site per let's say 1,000 megawatt electric plant. For nuclear power plant, you have 500 plus. Let's see why. If you look at the operations and training crew, for a natural gas plant, you need 20 people. For a new plant, you have over 7. Goes really back to strict training and oversight. So you can imagine in a nuclear power plant, in order to make sure all the actions of the operator is correct, you need multiple supervisors. And since you have multiple supervisors, your crew is bigger. Nuclear power plants operates 24/7, so you need multiple, at least 4 or 5 crews to cover the 24/7 shift. And then those 4 or 5 crews, you need training, so you need additional crew, couple of crews to just train them. And these crews always go on constantly doing tests. So if one fails, you need to have a really backup of a backup. So really it balloons up. Now, recent work by advanced nuclear community, particularly the new scale small modular reactor plant. Experience with the US NRC is shown that the regulatory commission that regulates nuclear is open to reducing this number of operational staff and yet keep the integrity. So you're gonna probably see a staff of maybe like 30 to 40 in the future instead of 100. Loss prevention is a huge difference compared to natural gas. In a natural gas plant, fizzles and flame, there's you see that, you hear it in the news, and then the next day you don't hear about it. The nuclear power plants, if you have radiation released to the environment, it's going to be a costly, very, very costly endeavor, as shown in Fukushima accident. And there's also about 100 security guards that are there to make sure there's not an invasion of the nuclear power plants by like other countries or terrorist groups. And then that's definitely, it's completely different than a natural gas plant. So for advanced nuclear, maybe if it's really small or has some certain features, you can maybe argue to go down all the way to 10, maybe, but at the end of the, you'll have to have similar level of security for different nuclear technology. Engineering, really here it becomes a difference in philosophy. These existing plants were built in the 60s and 70s, and they still operate, as I'll talk about, for many, many decades going on. And back then, the tradition was, including fossil industry, to hire, the local people, have a person dedicated to a certain. But nowadays, the kind of the thing to do, basically reduce cost and be more efficient. The vendor or have a subcontractor or have some kind of a remote operator. Nothing that nuclear technology that's gonna, stop it from doing that. Many countries in that have newer power, they do that. So it's really a different philosophy. So in advanced nuclear, we can definitely cut down the engineering. You're gonna still have a little bit more than a natural gas plant because the fuel engineering it is a more specialized field. On the maintenance side, again, similar to the philosophy, except for nuclear, you do have the radiation hazard. So you need to have physicists and some kind of people who understand the radiation and monitoring. So you're gonna need some extra people. So it boils down that for even the next generation, need a higher than a natural gas plant. So kind of losing the capital side because of all those other reasons and operation reasons. They're also going to be net, but it's not as glim as I pointed out. Thankfully, if you look at the LCOE distribution, a majority for nuclear power plant is for its fixed O&M and particularly on the capital cost, and the fuel cost is the variable and small natural gas. So we have an opportunity to even out if you're able to keep costs overall. The one thing I noticed that these typical percentages is extremely important to remember that these percentages only applicable to conventional water reactors, and they're not applicable to other reactors. For example, typical advanced reactors on average, their fuel costs are at least 4 to 5 times, or the variable and 4 to 5 times higher than conventional reactors. And I'll show you a plot with that. You compare it, actually, very similar to kind of solar PV. Solar PV, high cost and a little bit of fixed O&M. It's actually looking similar to a conventional nuclear power plant in terms of the distribution. But what's important at the end, what's gonna determine your economic competitiveness is actually having a magnitude here on this y-axis. So if you look at that based on some EIA data, what you see is that the nuclear power plant is almost twice the solar PV, as well as over twice the cost of a natural gas plant if you want to build a new conventional reactor. Seeing that, particularly what's grim about it is that under capital cost, fixed O&M and variable O&M, it's always going to be greater than PV, and that's of course it is because of near term, because right now the grid is relatively stable. And as you add more PV, it's going to lose its value. So then its cost going to also go up. But for now, near term, it's going to be tough to compete with these other energy sources. As I mentioned before, if the variable O&M is like fuel cost for almost conventional advanced reactors 4 to 5 times this, you can immediately see that their economic feasibility becomes highly reduced. The great news is that we have a great fleet of reactors generating 20% of the electricity, over half the carbon-free energy in the US, and they operate actually at $30 per megawatt hour. And you may ask yourself, well, why is that 30 current reactors versus if you have built a new reactors at 100? Because all these reactors have already paid off their capital costs. And so you can actually get very cheap electricity that's carbon-free. So it's very important to keep those reactors running. One thing that you see that studies have done, that this number can be even cheaper, and regulation takes almost a fifth of that, and half of it actually goes to a nuclear regulator, which is very different compared to these other energy industries. So let's look at the existing fleet briefly. One thing they've done in terms of reducing their cost is to keep going life extensions. They've already paid their capital costs. They constantly pay for addressing the spent fuel problem as well as decommissioning. They constantly, pay this fixed rate to a set fund. So if you keep extending their lifetimes, their economics, they continue to have very good economics. And almost all the reactors have gone 40 to 60 years, and some of the reactors actually recently have gone 60 to 80 years, which is great news. The other thing they've done is power operates. And what power operating does is that it takes that levelized cost of electricity and cuts it down, because you're basically using almost all existing equipment and infrastructure and just getting more juice out of your power plant. And that has been done since the 1980s, last 40 years. And we've done 8 gigawatt electric of carbon-free energy and saved basically 200 million tons of CO2 annually. And we've been able to do that by better understanding of the reactor power, as well as recapturing overly conservative margin, as I'll talk an example in the next slide for future power upgrades. And these power upgrades has been very cost effective. Their utilities have reported that they've gotten them on order of $1,000 per kilowatt, which on capital cost basis is competitive in natural gas. And of course, given the much lower variable O&M for nuclear, it becomes actually a very cheapest, basically almost dispatchable source of carbon-free that the US has ever realized. So it's a great way to continue to keep the existing fleet going. So I'll give you an example of what can we do in the future, and hopefully this example also tells you about my other message about how regulation is really stifling the economics of a nuclear. One of the things, these reactors are water cooled, and water has a certain upper limit where it can efficiently remove heat. And we call that critical heat flux. And the nuclear regulator assumes that that fuel rods, these are those pellets, and this is the scaled down fuel rod. If critical heat flux happens, the regulator assumes that there's an instant failure in this clad. Basically, you get a local hotspot, and your cladding gonna instantly fail. Now, physics-wise, what's going to happen? The cladding is going to go in high temperatures. You're going to have some localized hydrogen and oxidation pickup, and you're going to see basically what happens to the integrity of your cladding. One way to avoid this or give more margin to critical heat flux is to increase your flow rates, meaning basically get a bigger pump. And there's there's so much you can do to increase your pump capacity. So if you look at data out there of tests as well as real experience, you'll see that there has been never ever a single instant failure of a fuel rod when it undergoes critical heat. So that tells you basically this is an extremely conservative view of this thermal margin. It's as if you go and let's say you're pumping gas in your car, and the government tells you that you can only pump half full, because if you go full, your engine gonna combust. It's never happened, but the government's gonna force you to do that. And this is kind of a similar margin. And in fact, the industry has since Fukushima worked on developing more higher performing fuels compared to zircon. We looked at coated cladding. And you see that these claddings actually going to have much better mechanical performance at these temperatures relevant to critical heat flux. And if you look at what's the survival time of these fuel concepts, you can see that the current fuel can last almost 6 hours under critical heat flux. And this cold declining actually can last up to 4 days. So hopefully this is enough evidence that we can kind of remove these over-conservative margins that have been recognized, but the regulator has been really resistant to remove with these new advanced fuels that are kind of under commercialization in the next few years. And this is just one example of overall conservatism really limiting what nuclear's true potential. Now let's move on from the existing fleet to the next generation and the future of the industry. So if I think it's pretty clear, and you saw that from that EIA, LCOE projections, that unless we go to decarbonization scenarios where price of electricity is actually much higher, nuclear is not going to be competitive as it is today. So we need to make it commercial viable today in order to have a strong future tomorrow. In order to do that, we have to meet that market cost, which is around solar PV type of range, $60 going to go down. And at the same time, we have to minimize risk. We cannot have those experience with that large reactor that I showed you. And so to do that, what industry has done and the utilities, view and the community views is that we got to go smaller plants. Right? If you're a smaller plant, what happens is construction time goes up. It's just a smaller civil engineering construction project. There's less uncertainties, and the project management goes down against smaller projects. Unfortunately, what happens if we take the conventional reactor technology and go it down, it's the same thing as you see with fossil fuels or solar thermal. It's economy of scale. Your costs will go up, your O&M goes up because you have basically the same number of systems. So you got to come up with some kind of innovations to really overcome these. And at the time, those cannot, and keep your risk. That's what the industry has done and what we propose. So some of the things the industry has done, they try to increase the building power density for these smaller reactors relative to the large one through design or simplification. An example of design is they've taken these steam generator connected to a reactor pressure vessel with these piping and the pump, and they've actually integrated it all into one larger vessel. And that allows you to have a more efficient steam generator that allows you to remove accident possibility of these pipes burst, which for all you don't need that much power. That's one way to kind of improve the per watt performance. And this is similar to what the NuScale SMR, that's the only more or less advanced reactor that's been certified by US NRC uses. The other approach is through simplification. This is something the X300, which is an SMR designed by General Electric, has done. And they've basically taken the advantage of the lower power rating to remove a lot of these other additional backup water, because that's not necessary for this smaller thing. And now there's a whole lot of other solutions that has been proposed before even I was born, from range of digitization, robotics, advanced manufacturing, modular standardization, putting them underground, going high temperatures to improve efficiency. The question becomes, really where you should go. How do you choose, which is the most effective method? And so when you look at what our community, how they select, is they're inspired basically by the, similar to, that IA, the inspired cost breakdown that the larger reactors see. And so they choose, and they have to, come up with proposed solutions that address those issues. But then unfortunately what happens is the question becomes, can you apply those issues across these smaller water reactors, these non-water reactors? Are they applicable? So let's see even the large reactor. So within the large reactor, there is an advanced boiling water reactor technology perfected in Japan. And technology actually has been over and over again built in modern era under 4 years. And in fact, it has a record, 3.1 years. It continues to be a record for a nuclear power plant construction. And it experienced a cost that is much lower than those two plants that are currently being constructed in the US. And in fact, this power plant has the concrete per megawatt electric produced compared to those power plants that are being constructed in the US. So you can see immediately that I cannot take and this breakdown apply it to even factors of same. Another empirical evidence is that if you look at what is the most expensive nuclear technology that has been connected to the grid recently, expected to be connected to the grid in the next 5 years, and it's actually those Russian small reactors, small modular reactors that are purely fabricated in a factory. And you can see that they're attaining 24 cents per kilowatt hour or $240 per megawatt hour. That'd be much more expensive than those plants that are being built in Georgia. And you ask yourself, well, why? Because I thought production is going to be cheap. Well, there's always first of a kind issues first. And secondly, what you see here is they lose so much in economy of scale, 35 megawatts versus 1100 megawatts, that you end up with a much, even though you reduce your risk drastically by factory producing, you've increased your cost so much. So that tells you really, we gotta really come up with solutions that are actually applicable to the individual reactor. And that's why, to understand what are the cost drivers of individual reactor systems, what we've done recently, we've actually bottom-up models for these type of reactors, and then come up with the best solutions. And these cost models that we've built is based on 1,400 plus cost data based on recent and historic databases. We've done successful benchmark with vendor data, with public information, realized project costs, as well as some proprietary costs. And we plan to open source this tool next year. Currently, it includes all major near-term small modular reactors. And currently, we're expanding it to gas-cooled technology, sodium, salt-cooled technology as well. We're focused on this near-term water-cooled SMR because if you just look at nuclear supply chain, that these are the reactors that are going to out of the gate for commercialization by 2030s relative to the other types. And what this allows us to do is to evaluate, propose cost-effective technology innovations of pathways, as we've done in this case for a water-cooled SMR, looking at different of those proposed solutions, looking at the cost breakdowns, and seeing basically which one is more effective. And some of these solutions that you can see, they're basically make almost no difference in the total overnight capital cost in this. So I'll give you an example of what is one of these innovations. One is something I proposed over 10 years ago, was to, instead of looking at these shell and tube steam generator, why don't we replace them with these more modern plate type steam generators that has been really perfected as a plate type heat exchanger in chemical industry. And the resistance immediately was always, what happens with these smaller channels and what happens with blockage and all these other things. But since then, there's been a lot of testing, there's been a lot of work, and actually one of the SMRs in France is a SMR concept developed by EDF, actually adopts this as a base technology. And what this allows you to do is you're allowed to now remove so much more heat from the reactor vessel and really take that advantage of the higher energy density that fission allows you to do, and really improve your power density given the same release structures. And that's going to really help with cost reduction. So when you implemented this and look at the range of condition, we get range of costs, and I'll discuss shortly. So one of the first thing we see is that the economy of scale, because we've gone from over 1,000 megawatt plant to a 170 megawatt electric plant, it is going to increase our costs, particularly our O&M costs going to be huge, because we have more or less similar systems, and it's very hard, as I showed you, to argue that you can really reduce your staff to single digits, and so my O&M cost is pretty high. So I have to really improve this, and the way we can do this is through looking at how can we get more juice out of, again, same structures. And we can do this, and one of the first things we can do is we can reduce this grace period. Now, what is this grace period? This grace period basically tells you that if I have none of my safety systems that are actively powered, no power from the grid, no outside help, I have 2 weeks till my reaches fuel demand. Now, all that over 400 reactors operating today, none of them have even close to this type of profile. And so why would we propose to have such a drastic, such an incredible safety performance when the possibilities is very minute. Currently, if you look at recovery times for after you lose power to grid, we're talking about 3-4 days. Why do I need 2 weeks? And so if we remove that, let's go for a week, which would be again an improvement over all the 400 reactors operating today. We can improve that power rating and we can drastically reduce the cost. And you can see on FOK cost, we're approaching about $70. And for nth of a kind cost, we can actually get to that $60 per megawatt hour that we want. Now you look at, what about other technologies? This technology, we can do it with water-cooled SMRs, whether it's a PWR with a compact steam generator or a forced circulation with a boiling water reactor. When you ask non-water reactors, they're currently rated at greater than $100 per megawatt hour. One of the reasons is that their grace period in some cases are actually infinite. And so when you have such a huge great safety profile, you're gonna pay for it in somewhere, and that's really a big economic driver. The other thing you see that, can we even go further? Can we go beyond $60? Yes, we can, because right now that $60 is limited by that critical heat flux limit that I already told you how over conservative it is. All right, so now I'll end with few insights as well as list of my top innovations. So one of the insights, first insight is that in order to really attain these economics, we needed a pump. We needed a pump to add to the design flexibility. All right, and however, today, if you look at in the U.S., most plants, most SMR proposed plants are natural circulation or gravity driven. And when you look at where they came from, where this idea of no pump for operation came from, really was born out of an era in the late 80s and the 1990s when there was a huge anti-nuclear movement. The public perception was low, and there was really not a big challenge to nuclear economics. Today, the case is almost switched. We have actually more than 50% support from the public, but our nuclear economics is highly challenged, and that's what you see. All the U.S. products are natural circulation versus all the international products are forced circulation, and that's the ideology has taken our hand. The other insight is that to really get to that $60 or roughly $3,000 per kilowatt overnight cost, have to focus on reducing direct costs. We cannot abandon reducing that direct cost, particularly for advanced reactors. Some of their components are greater than 10% of this target capital cost in order for nuclear to be economical. So manufacturing becomes very. The other one is that as we went larger, particularly with that experience with Japan with the advanced boiling water reactor, it's a 1,400 megawatt electric plant. As we kept going larger and larger in size, modular construction became more and more necessary to keep the project risk down and project management and schedule to a reasonable level. Now with the small reactors, we've actually reduced that size quite a bit. So we don't need as much new construction techniques or too intensive modular construction, because we have already, in some cases, drastically reduced the amount of construction that takes place. And there's modularization in any industry. If you look at it, takes an overhead. Natural gas plants really started modularizing once again. They scaled up to 800, now even like 1,000 megawatt electrics. So that's that focus has to be done properly per plant. Now to my top 3 innovations that's going to make a difference is performance-based regulation, radiation protection. I've already talked about this, that we treat radiation hazard completely different than other forms of hazard. And then the next thing is, as I just mentioned, cost-effective manufacturing is critical. If you look back at that table, what you see is above that Russian floating plant, you have the Chinese reactors that are coming out at very, very cheap price, because labor in China is cheap, as well as the products in China is cheap. Today, if you want to buy a valve for a nuclear power plant that has nothing to do with actual nuclear hazard, we cannot do that because of export control rules. So we have to kind of overcome this unfair field. And the last one is, high performing materials are always going to be important, because power density, temperatures is going to be the first order impact on the economics of a power. With that, I'll end my time. Thank you.